Hey guys, this video is going to be all of 2.2 through 2.4. I'm going to lump them together since this is just review. So what we're going to do in these sections, we're going to be taking derivatives, and we'll, in 2.2, review the product and quotient rule, and then 2.3 will be the higher order derivatives, and 2.4 will be the chain rule. We'll say, well, the product rule says that if you have two differentiable functions f and g, then the derivative of their product is the derivative of f times g plus f times the derivative of g. Right? So you take the derivative of one multiplied by the other, and then add the one multiplied by the derivative of the other. I usually say something like the derivative of the first times the second plus the first times the derivative of the second, and however you want to do that. Notice that since we're adding, we could do this in either order, and since we're just taking the derivative of one, it doesn't matter which way you do that. You just have to remember it's something like the first times the derivative of the second plus the second times the derivative of the first, or however you want to remember that. But there it is. That's the product rule. Let's find f prime for this function f of x. So what we'll do here is let's identify the first guy and the second guy, and we'll use the product rule to take this derivative. So what would f prime of x be? Well, what it's going to be is, I'm going to write it like this first. You could think of it as the derivative of the first times the second plus the second, the derivative of the second, times the first. And again, you could do this in either order. You could flip these guys, but however you want to do that. All right, so what's the derivative of the first guy? So 2x to the fifth becomes 10x to the 4, plus x is plus 1, and minus 1 goes away. So that's the derivative of the first, and then we copy the second one down. So derivative of the first times the second, plus the derivative of the second, which is just 3, times the first, which is 2x to the 5, plus x minus 1. And there it is. That's the derivative of f of x using the product rule. You take the derivative of the first guy times the second guy, plus the derivative of the second guy times the first guy. And you don't need to simplify that or do anything with it. Just leave it as is. All right, so what about the quotient rule? We introduced that or used that word. So that, remember, is... remember from before we had two differentiable functions. We were going to multiply them. So the quotient rule is when we're going to look at their quotient, right? We're going to take the fraction f over g and divide them, right? So here is that rule. So for f over g, when you want the derivative, you do g times f prime minus f times g prime over g squared. So I always think of that as the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Right, and that's just one of those things you need to memorize. Here's h of x. Let's find h prime of x. Right, so here is the top, and here is the bottom, top, bottom. So what is the derivative? Notice that this is a quotient. It's a one thing divided by another. There's an x in the top and an x in the bottom, and so we'll have to use the quotient rule. So it's the bottom, copy that down, 2x plus 1, times the derivative of the top, 5x to the 4 becomes 20x cubed, minus 3 goes away, so that's all there is. Bottom times the derivative of the top minus the top, copy that down, 5x to the 4 minus 3, times the derivative of the bottom, which is just 2, and then you divide by copying down the bottom, putting parentheses around it, and squaring it. You do not need to simplify or do anything else with that. There it is, the derivative using the quotient rule. All right, this says find the equation for the slope of the line tangent to the graph of y equals this guy, right? So slope of the line tangent, you should think, oh, that's the derivative. And so finding the equation for that is just another way of saying find y prime, right? So find y prime. Notice here that we have a quotient minus something else. So since we're subtracting, we're going to find these derivatives separately. And when we call that term by term, right? You can find the derivative term by term. And for that first guy, we're going to have to use the quotient rule because it is a quotient with an x in the top and the bottom. Right, so remember quotient rule was the bottom, copy it down, times the derivative of the top, minus the top, times the derivative of the bottom, over the bottom squared. So 7 minus 3x, put parentheses around it, and square it. Right, notice this 2, derivative of 2x is just 2, and this negative 3, the derivative of 7 minus 3x, 7 goes away, you're left with the minus 3. Okay, so that's just the first term. Then we'll have to subtract. What's the derivative of 6x to the 5th? Well, that's 30. 6 times 5, x to the 4. And you can just leave that like that. All right, there it is. Sorry, recently opened a hair salon and has found that her profit can be modeled by this function p of x, where x represents the number of customers she sees. Specify and interpret the expected marginal profit when Penny sees 10 customers. Right, so what that means, specify, that's just find the marginal profit when she sees 10 customers. So remember, marginal profit is p prime. And if we're seeing 10 customers, then we're looking for p prime of 10. So that's what we want to find first. And then we will interpret it. But let's find it first. So to find p prime of 10, we need to first find the derivative p prime of x. And then we'll plug in 10. So what's p prime of x? So here we'll use the quotient rule. We have the bottom, just x, times the derivative of the top. So x squared becomes 2x, plus 3x becomes plus 3. That's a 3 there. And then plus 1 goes away. So bottom times the derivative of the top minus the top. Times the derivative of the bottom, which is just 1, over the bottom squared. All right, and that is the derivative of the profit, p prime, the marginal profit. So now we want to plug 10 in. So what is p prime of 10? Well, that's going to be 10 times 20 plus 3. 20 plus 3 from that 2x plus 3. So 10 times 20 plus 3 is 23. Minus x squared, so that's 100 squared would be 100, plus 3x, which would be plus 30, plus 1, over 100, again from x squared. Okay, so now let's simplify that. Well, that would be 230 minus 131 over 100. 230 minus 131 is 99, so this would be 99 over 100, or 0.99. So when Penny sees 10 customers, her marginal profit will be 0.99, but what does that mean? Let's interpret that. I'm not going to write that down, but I will just say it. So the interpretation of the marginal profit, remember that's approximating the change in profit when the input increases by 1. So since the input is number of customers, this 0.99 being a positive 0.99 is an approximation that her profit will increase by 0.99 when she goes from seeing 10 customers to seeing 11 customers. All right, so that 11th customer will increase her profit by approximately 1. Quotient rule. So let's dive into 2.3. It's over higher order derivatives. So we'll look at what are higher order derivatives. We'll look at notation and interpretation, and then we'll use first and second derivatives to do things. So first, what is higher order derivative? Well, remember that if we have a function, we can find its derivative f prime. And since f prime is also a function, we could find its derivative, which we'll call f double prime. Just put 2 primes there. We call that the second derivative of f. The second derivative of f is still a function, so we could find its derivative and find f prime prime prime, or f triple prime, which would be the third derivative of f. And you can just keep doing this to find the fourth derivative and the fifth derivative and whatever, blah, blah, blah. Assuming, of course, that the function that you're trying to take the derivative every time is differentiable. And we'll look at ones that are only. But that's the idea of higher order derivatives. You're just taking the derivative of the derivative, or if you're taking the the third derivative, you'd be taking the derivative of the derivative, whatever. All right, so the higher order derivatives is taking a derivative and then just taking the derivative of that thing. So here's some notation. We'll really only look at the first and second derivative, but here I've got the nth derivative, so you could plug in any number you like for n there, and that would be the same notation. So for f, if that's your function, then the first derivative, this box should be familiar to you already. That's f prime. For the second derivative, we would just put a second prime there, call that f double prime. And then usually after that, like f, instead of triple prime, maybe you would do that one. But after that, that's too many primes, so you would just put like 4 in parentheses. And so we say the nth derivative would be just f and then upper n in parentheses. And that would say take the nth derivative. More notation, again starting with f, we could denote the derivative by df dx. The second derivative, you would put a square on the d and a square on the x. So I'd be taking two derivatives with respect to x both times. So that's why there's a 2 on the d on the top and an x in the bottom. And if you want to take the nth derivative, this would say take the derivative n times with respect to x n times. And so that's why there's an n on the d and on the x. And then same thing here with the y. It's just a y instead of an f, but these two are the same. All right, this is what we'll use the most, is just f prime, f double prime. It's just easier to deal with. Or do some examples here. If f of x is that, find f prime of x. Okay, what's f prime of x? So x to the 4 gives us 4x cubed. Minus 3x squared gives us minus 6x. Plus 4x gives us plus 4. Minus 100, that's a constant, and it goes away. All right, what about the second derivative, f double prime of x? Well, that means we're going to look at this function, f prime of x, and take its derivative. So 4x cubed becomes 12x squared, and minus 6x becomes minus 6, and plus 4 goes away. All right, it also says find f triple prime, or the third derivative of f. And for that, we're going to look at f double prime and take its derivative. So 12x squared gives us 24x, and minus 6 goes away. All right, now find f upper 4 of x. That would be the fourth derivative. And to do that, we go to the third derivative and take its derivative, and that would be 24. All right, and then it also says find the nth derivative if n is greater than 4. So what would f5 be? Well, for f5, we would look at f4, which was 24, and take its derivative and get 0. And then if you took the derivative again, the derivative of 0 is still 0. Do that again, still 0. Do that again, still 0. So that thing would be equal to 0 if n is greater than 4. And that's because 4 was the highest degree of this polynomial. Whoops, I didn't really box that, but that's okay. So if you take these polynomials, you can take the derivative as much as you want, but eventually they just start being 0 all the time. Okay, so here's another f of x, and we want to find the first three derivatives. So f of x is 2 over x, so to find the first derivative, what we'll do first is rewrite f of x as 2x to the negative 1. And then that's going to make taking the first derivative easier. So what's f prime of x? Well, we have 2x to the negative 1 is going to become minus 2, right? 2 times negative 1. X to the minus 2, negative 1 minus 1. All right, now let's take the second derivative. So to do that, we're going to come look at f prime and take its derivative. So we'd have a negative 2 times the exponent negative 2 gives us positive 4. X to the negative 2 minus 1 would be negative 3. And now f triple prime of x, you look at the second derivative and take its derivative. So you do 4 times negative 3 to get negative 12. X to the negative 3 minus 1 would be negative 4. So that would be the third derivative of f of x. Now let's interpret these higher order derivatives, right? We've been taking them, but what do they mean, right? So remember, f prime describes the rate of change, right? It's the rate of change of f. It's the slope of the tangent line. The second derivative would tell you the rate of change of f prime, which would be the rate of change of the rate of change of f. And these things would tell us about what the function looks like, right? So this we'll start talking later. The rate of change, we'll talk about how it's increasing or decreasing, right? It could be going up or going down. And that second derivative will tell us something called concavity, which tells you how the change is happening, right? If you're going up, how are you going up? Are you increasing and then increasing how you're increasing, or decreasing how you're increasing, whatever that means. But the point is that the first and second derivative can tell you a lot about what the function looks like, and going forward we'll use things like increasing and concave up or concave down, whatever that means. So let's use a real world example here. So let's say you're driving your car, and f of x tells you the distance you are from your house after x minutes. Let's assume you're going to just go in a straight line and run over whatever's in your way, because why not? So f of x is your distance away from your house. So f of 4 would tell you how far away you are at 4 minutes, something like that. What would the derivative represent, right? So f of x tells you your position, your distance. The derivative of f would be your rate of change. So if you're in a car, usually that's given as miles per hour. That's your speed, right? Your rate of change of your distance over time is your speed. Miles per hour is what we usually use. What does it mean if that is positive or negative, right? So this would be your speed, usually miles per hour. What does that mean if it's positive or negative? Well, if it's positive, that would mean you're getting farther away, right? You're moving away from your house. If it's negative, that would mean your speed negative would, in this case, mean you're getting closer to your house, right? So maybe you're going backwards. Let's assume you hopefully turned around, but maybe you're just reversing, right? You can think about it like that. Your speed is negative, means that you're heading back towards your house. All right, now what about the second derivative? What would that represent? Right, so we're talking about then how your speed is changing. And what word do we know that means how your speed is changing? Well, that's your acceleration. Right, your acceleration. So you can, for example, if you barely press on your gas pedal, you'll move forward, but you'll move forward slowly. So maybe your speed is increasing, but everyone will get mad and honk at you because, like, come on, dude, let's go, right? But what if you floor it? If you floor it, you'll just take off, right? Your speed's increasing, but it's increasing very, very quickly. That's the idea of your acceleration, something like that, right? You can increase your speed and do it at different rates, and that's what the rate of change of the rate of change means. The rate of change of the first derivative, something like an acceleration. So if your acceleration is positive, what does that mean? Well, that means that you're increasing your speed, like you're flooring it, right? You're moving forward and moving forward faster. If your acceleration is negative, that would mean that you are decreasing your speed if you're moving away from home, right? You're maybe coming to a stop at a stop sign. Or if your speed is negative, that would then mean that your speed is becoming more and more negative. So let me say that one more time. If your speed is positive, you'd be going away from your house. And then if your acceleration is positive, that means your speed is getting more and more positive. So that would be like you're heading away from your house and increasing your speed. But if you're heading away from your house and your acceleration is negative, that means you're slowing down. Right? So that would be like you're coming to a stop sign. So that's sort of the normal way to think about that. But then the alternative is, what if you're returning home? If your speed is negative, then the things are flipped. Right? If your speed is negative and your acceleration is negative, those are sort of together, and that means you're heading home faster. And that's the basic idea. We'll interpret that here in a better context. So what we were saying with that about interpreting that second derivative can be summed up in these next couple slides. So if f prime and f double prime, you can think about that as sort of your speed and your acceleration. Later we'll use increasing or decreasing and concavity, whatever that is. Then we say the function is changing at an increasing rate. So same sign, increasing rate. So if f prime and f double prime are both positive, well, f prime being greater than 0 means the function is increasing, right? So the speed, the rate of change, is going it is positive, so your function is sort of going up. It's increasing. And since that second derivative is also positive, they have the same sign, then we say it's an increasing rate. If f prime is negative, then we say the function is decreasing, right? The slope is negative. As you go to the right, it goes down. It's decreasing. But if the second derivative is also negative, they're the same, so we say it's an increasing rate, right? So same sign, it's like multiplying numbers, gives you increasing rate. Whether they're both positive or both negative, same sign, increasing rate. If they have opposite signs, then we say it's a decreasing rate, right? So if f prime is positive, the function is increasing just like before. But if f double prime is negative, that's the opposite, so we say it's increasing at a decreasing rate. If f prime is negative, then the function's decreasing just like before. But if f double prime is positive, that's the opposite, so we would say the function is decreasing at a decreasing rate. Again, this is like multiplying numbers. If they have opposite signs, the first and second derivative, then that would be a decreasing rate. No matter which one the signs are, it's a decreasing rate if they are opposite signs. Let's look at an example here. So it says the number n of cookies, which is what we call treats, that Sully eats in a day. You know, it's more fun to call them cookies and treats. Like everyone calls them treats, but cookies is just like, oh, cookies, yay. I don't know. Anyway, the number of cookies that Sully eats in a day is given by this function, where p is the price per cookie, right? And so maybe if they're really expensive cookies, he's not going to get as much, or if they were like free on the side of the road or something, then I'll give him a lot, whatever. So that function takes in the price and spits out the number of cookies he gets per day. So find the first and second derivatives. So let's find n prime of p. Looks like we get minus 0.1 p. And the second derivative, n double prime of p, would be minus 0.1. All right, then it says, what is the trend of n of p when cookies are $4? So whenever you see that, what is the trend? That means you need to plug in that number it gives you. What do we get? Minus 0.4 for the first derivative. Plug it into both. And in the second derivative, you get minus 0.1. Now for the trend, you always want to say something like increasing or decreasing at an or a increasing or decreasing rate. That's what that should always say when it says what is the trend. This thing is given by the sign of the first derivative, something like f prime. So over here, since this was negative, this is going to be decreasing. And then at a blank rate comes from where you compare the first and second derivative signs. So the second derivative is negative. These are the same sign. So same sign gives us an increasing rate. So decreasing at an increasing rate. If they were opposite signs, we would have said at a decreasing rate. And if n prime was positive, we would have said increasing at whatever rate. But that's always the way you want to phrase that when it asks what is the trend. All right, that's the end of 2.3. Okay, now on to 2.4, we will talk about the chain rule and the general power rule, whatever those are. So let's do that. So the chain rule and general power rules, right? So they're something like this. So we know how to take the derivative of something like y equals 3x squared plus 9, right? That would be 6x. But what if you want something a little bit more complicated? How would you take the derivative of that? To do that, we'll have to use what's called the chain rule. Notice that these are compositions of two functions. We have an inside function and an outside function. And we'll talk more about that. So let's start with the general power rule. Right? So that says if u is a function of x and y is a function of u, then we can talk about the derivative of y with respect to x, dy dx. So u is a function of x, y is a function of u. That means we can talk about y as a function of x by looking at y of u of x. And we should be able to find the derivative of y with respect to x. So that's all that says. So now let's say that y is actually specifically u of x to the n, right? So that's this guy. Then the derivative dy dx is this guy right here. n times u of x to the n minus 1. Right, so notice that we did the normal derivative if that u of x was just an x, where we brought the n down and decreased that, and we left this thing alone, and then we multiplied by the derivative of u with respect to x. So that's the general power rule. It says if you have something raised to the n, to take the derivative, you bring the n down, leave the something alone, decrease the derivative, or I'm sorry, the exponent by 1, then you multiply by the derivative of that inside. Right? So I always think of that as taking the derivative of the outside, and in this case that is the power rule, and then multiplying by the derivative of the inside. Here, that y we can think of as a composition of two functions, f of x and u of x, where f of x is that outside function. It's on the outside. It's the whatever to the n. And u of x is on the inside. That's the inside function. So we always take the derivative of the outside and multiply by the derivative of the inside. So let's see that in action. So it says identify u of x and find dy dx. So what was u of x? U of x, that's this piece in here. It's the stuff raised to the n. In this case, n is 4. So u of x is 3x minus 2. So to find dy dx, we know that we're going to use that rule where you do n times u of x to the n minus 1 times du dx. So to do that, we need to find du dx. So what is du dx? Du dx is the derivative of u. So this guy looks like you get a 3. So now let's just plug that in, where n was 4, so this would be 4 times, and then we copy down u of x, 3x minus 2. 4 becomes a 3, 4 minus 1, times 3. So there is dy dx. All right, now let's talk about the chain rule. So the chain rule is a generalization of that general power rule. And that's where you can take the derivative of any two functions, no matter what they are. Before, we had the outside function was that x to the n. Here, the outside function is just any f. And the way you do that is you take the derivative of that outside function, you leave the inside guy alone, and then you multiply by the derivative of the inside function. Right, so that's the chain rule. Right, and like I said, this is just a generalization of the general power rule. So the general power rule is a special case of the chain rule where f of x is x to the n. So here's some alternate notation. If y is that composition like before, then you can write y equals f of u and u equals g of x. And then the chain rule is written like this. dy dx equals dy over du times du over dx. So this is again just sort of the derivative of the outside times the derivative of the inside. So now let's say that y is u cubed plus u and u is 3x minus 1. Let's find dy dx. I want to do this in two ways. So the first way that I want to do it is by recognizing that dy dx is going to be dy du, because y is a function of u, times du dx, because u is a function of x. So first let's find these two pieces, dy du. So that's going to means go to this y equals u cubed plus u and take the derivative with respect to u. So we're going to treat u as our variable. So looking at that thing, if we take the derivative of u cubed, you do the same thing like it was an x, but you treat u as the variable. So u cubed, take the derivative. Whoops, look at me, I almost wrote an x there. Is 3u squared. And then plus u, when you take the derivative, you get plus 1. So that's dy du. We also need du dx. So for that, we go to this u equals 3x minus 1, and we take the derivative with respect to x, and we get 3. So now dy dx is those two things multiplied together, so that's 3u squared plus 1 times 3. And the last thing we want to do is plug in what u is. Right? If we want dy dx, we want just an x in there. So that would be 3 times, and then plug in 3x minus 1 for u, squared plus 1 times 3. So there's dy dx. Now I want to do this another way. So my other way is going to be, notice, so from here to here, we plugged in u equals 3x minus 1. Well, we could do that from the very beginning. So let's do that. Let's just go ahead and plug u in. So what's u cubed? That would be 3x minus 1 cubed. All right, plus, what's plus u? Well, that would be plus 3x minus 1. Then dy dx is just the derivative like normal, but we're going to have to use the chain rule. Right, so derivative like normal means we're just going to take the derivative of this thing. We don't have to deal with this u or anything like that. But when we come to a chain rule, we'll have to take the derivative using that, right? Whatever that is. All right, so that's going to happen here with this first term. We've got something that's not just an x, it's 3x minus 1, raised to the 3. So the way we take that derivative, that's the general power rule. We do the derivative of the outside, so that would be 3 times the stuff squared. And you leave that stuff on the inside all alone. Then you have to multiply by the derivative of that inside, so the derivative of 3x minus 1 would be 3. And then you add just the rest of it, so the derivative of 3x is 3, and the derivative of negative 1 is nothing. Right, so that's another way to do this. And notice that these are really the same, right? If we took this and distributed this 3 through, we would get 3 times 3x minus 1 squared times 3 plus 3 times 1, which is 3. And those are the same. So it doesn't matter how you do this. I prefer this method of just plugging it in first and doing the chain rule when you come to it. Let's look at an example here. So it says the demand for pennies, pies, D, depends on the price per pie, P, by this function, D of P is 10 plus P squared. Then it says the cost per pie sold, C, depends on the demand by this function, C of D. Right, so the demand depends on the price, right? Different price, you sell more or less. And the cost per pie depends on the demand. So the more that they buy, the more you sell. Maybe the less it costs per pie, something like that. Anyway, so it says, what would show how the cost of producing a pie changes with the price per pie? So how does the cost change when the price per pie is changing? So that would be something like a cost over price. But not just cost over price, right? Not that. Because we want to talk about how these things are changing. So what that would be is the change in cost over the change in price. dc dp, the derivative of the cost with respect to p, the price. So that's what we want to find. What would dc dp be? So we could do this again 2 ways. We could find dc dd, right, by finding the derivative of c with respect to d, and then multiply that by d dp by finding the derivative of this guy. Or we could just compose these things from the beginning, which is how I want to do this. So what we're going to do is find c of p by plugging in d of p wherever we see a d in the c equation. Hopefully that makes sense. So we're going to this cost function. What is it? Well, it's 20 plus d to the negative 1. So what we're going to do is plug in d of p, right? So that when it says d, it really means d of p. And what is that? Well, let's actually plug that in. So that would be 10 plus p squared to the negative 1. Now to find dc dp, the derivative, we're just going to take the derivative. Right, so what's the derivative of 20? Well, it goes away. And then we need to take the derivative of 10 plus p squared to the negative 1. And to do that, we'll have to use the chain rule. So what do you get? Well, you're going to get negative 1 times whatever to the negative 2. So that's the derivative of the outside. And when you do that, you're going to leave the inside alone. 10 plus p squared stays alone, as it was. Then you multiply by the derivative of the inside, which would be 2p. So there is DCDP, the change in cost with respect to price, which is what we were looking for. So then it says, how does the cost of production change as price increases from $1 to $2? And what we want to do is approximate this. So this would be a marginal change. If you found this exactly, you could, but I'm going to approximate it. On an exam or something like that, it would say approximate, and you would have to use the derivative. But remember, that's marginal change, and so that means we're going to take this $1, the original, the lower guy, and plug it in for P. And when you do that, you get negative 1 times 10 plus 1 squared is 11 to the negative 2 times 2 times P is 1. So that's negative 2 over 11 squared, which is 121. And that is how the cost of production changes as the price increases from $1 to $2. So it decreases, but just very slightly. End of 2.4, chain rule.